This tutorial is part 2 of 3. In the previous tutorial we discussed Gaussian mixture modeling based on looking at a generic data set provided by Spark. Here we're going to look at a different data set which has two variables. It looks at the length of an eruption for Old Faithful, and it looks at the length of time between eruptions, trying to understand, are there underlying distributions in this data that help us understand perhaps different types of eruptions depending on time of day. So again, we're going to import from PySpark. We're going to import our Spark context and the Gaussian mixture model. We're going to define the file path. In this case, it's called faithful.csv. And we're going to call this input object, the RDD, faithful data. So if you run through both of these iterations, and just to double check that we have the right data in here, let's look at take. So this is what you should see. A couple of things to note. The data are comma delimited. In the previous tutorial we dealt with spaces, so keep that in mind as we think about formatting this to actually train it for Gaussian mixture modeling. So what we're going to do here is we're going to create a formatted data object called formatted faithful data, and to do this we're going to call faithful data and we're going to map. And again, reminder that this map allows us to call this on each line. So we're going to do lambda line, and we have the purpose of this piece of code is we want to ensure that each one of these numbers is interpreted as a float type in Spark. It is necessary to run these algorithms, and while it's certainly possible that Spark interpreted these by default in that way, this line makes sure that that is the case. So we're going to say for x, or the object, in line.strip, so we are stripping each line, and then we are splitting based on a comma. And what we're doing then is we're saying, okay, for each object in this faithful data RDD, make sure that it is a floating point. So if we do formatted faithful data and we see and typically there's always a mistake you're going to run into. So in this case, the mistake was not putting quotations around this comma here. Make sure that you do. And in that case, well, we appear to still not exactly be doing the right thing. So what did I forget? This is not only a useful exercise just for you to laugh on video, but also for thinking about calling a for loop. We need the in command here. So if we've created this object now successfully, we should see things that are in floating point value, which is exactly what we do see. So let's consider what we should do next. Now that we have the data in the right format, we are going to create a Gaussian mixture model, and to do so we're going to call, perhaps unsurprisingly, the Gaussian mixture model, the Gaussian mixture function .train, and we are going to do this on the formatted faithful data. Be sure that you call the formatted data. And if you recall from the first tutorial, what is going on here is we need to decide exactly how many underlying distributions we believe there to be. In this case, we are just going to work with 2. You can certainly select more, and in the next tutorial we will actually look and see what happens when we do that. So it is going to take just a little bit to process what the functions are. And again, when you've created this object, in other situations you might be interested in looking at the training error or the accuracy of the particular model. This is not a supervised algorithm, so all that we can look at are the distributions that were produced by the model. So we can say for, and this is saying this is setting up a loop to loop through both, make both normal distributions that were produced by the model. We're going to print the weight, and in this case we have the GMM model faithful weights, and this is weighting on that particular distribution. So it's going to correspond to I, so this iterates through both. And for each of these distributions, we want to find certain things. We want to know what is the mean. That is because for these normal distributions, again, we have two parameters. We have the mean and a measure of variance. And so to get these, we need to explicitly call them on the object that was returned. So if we have this, we're going to call it mu. And we're going to call, again, the variance. So again, from the model that was returned, we're going to call Gaussians, and I, that's sigma. And again, this array part is something we do just to make things display better. But if we look at this particular piece, you should notice that I had initially missed identifying what this was, and that wouldn't necessarily keep it from printing, but having this step in here is going to make things a lot easier to read. So we can see that the model parameters were returned. We have vectors for both the mean and the variance, and so of course typically you would not stop here, that you would want to use this to actually go back and look at perhaps the context from which the data arose. But this is certainly suggesting that there are plausibly at least two underlying distributions present in this data. And to keep in mind, this is an unsupervised algorithm, so you're not going to necessarily see something nice and neat and be able to say, this model is better than using three underlying distributions.